Please.
So at this point, good evening, everybody, and it's tea time. So I'm Marco Ballarin, a PhD student from the group of Professor Montangero at the University of Padua, and I'm gonna present Qmatchatea tensor network emulator for quantum circuits on Leonardo. So, in general, what we want to do is run some quantum algorithm with our devices. The best possible thing to do is to run it with real quantum hardware, but the problem is that it's noisy and that there's a limited amount of qubits. Actually, there has been incredible success in the last week and improvement on this part, but still it's not on the level of being able to run any quantum algorithm. Or we can use an exact simulator that tracks the state vector, but it has the problem of an exponential scaling with the number of qubits. So it's difficult to use. QQuantum with the QTensorNet is another possible thing, but even there are some problems. You can simulate any circuit. There are even other type of simulator like Clipper simulator that let you simulate a high number of qubits, but not any circuit in particular, those with a reduced number of T-gates. And what I'm gonna talk today is a tensor network emulator that lets you simulate a high number of qubits with the cost of flexibility on the entanglement. We can only simulate bounded amount of entanglement. It's of the same kind that it was discussed yesterday. So the whole idea is that, yes, the Hilbert space of n qubits is exponential, but we can represent a subset of this huge Hilbert space efficiently. And the whole idea of tensor network is, let's say, to use the Schmidt decomposition, if you're familiar with that. So we are gonna highlight two subsystems, the subsystem A and the subsystem B, and those are gonna be connected by the Schmidt coefficients that represent the quantum correlation between the two subsystems, and we are gonna compress this coefficient in order to compress the entanglement and have the best possible approximation of the state in terms of the entanglement. Indeed, we are only going to keep the chi most important Schmidt values, the most important simulators. And if we are gonna let's say, iterate this procedure of dividing into subsystem our quantum state, we end up in the matrix product state scenario, where each of the qubit is represented by this circle, which is a tensor, and the connection between qubits are encoding the quantum correlation between them, and in particular, those are bounded by this bond dimension chi. What is really important is that now the memory requirement passes from an exponential in the number of qubits in linear with the number of qubits and quadratic with this bond dimension. Something that I really want to stress, there is no free lunch. If you want to represent a general quantum state with volume low entanglement, so the maximum entanglement possible, well, then your bond dimension is gonna scale exponentially with the number of qubits, and you're gonna end up with the same scaling you had before, plus some overhead. But once we have our matrix product state, we can contract quantum gates to it and effectively emulate any quantum circuit up to a certain entanglement. So the really important message is that matrix product state simulations are not limited by the number of qubits, but by the entanglement in our state. Something else I want to stress is then the tensor is more or less, let's say, a matrix whose dimension is chi, and it is important later on for the system. Then in Qmatchatea, there are some optimization and parallelism going on. For example, gates are really easy and really cheap to contract between one another because they are simply 4x4 matrices. That's basically free, but contracting a gate with the MPS, it's not easy and not cheap because we have that bond dimension that can be very high. So what we do is that first we contract together gates that act on the same 2 qubits. Why? Because we are not constrained, as in a real scenario, to a basis set, but for us, those are just matrices. I don't care how the matrices are composed. And then we can split MPS between different nodes and so employ some parallelism, which is very nice for current and HPC devices like Leonardo. Obviously, we will have to put some barriers, some communication between the nodes, but it can be done. It's not so straightforward because there are some algorithmic subtleties in tensor network algorithms for the parallelization, but it can be done. And what is really cool is that Qmatchatea is on Leonardo and it's super easy to use. So you can log in on your Leonardo profile, load the profile quantum and load the Qmatchatea module. And then even running a simulation is pretty easy because you can build your quantum circuit using Qiskit. You define which observables you want to measure. For example, here, the projective observables are just projective measurements of your circuits. You define your convergence parameters, so the important parameters that are gonna control your evolution, in particular the maximum bond dimension, which was what I was telling you before, what is gonna bound the dimension of our state and also the goodness of our approximation of our run. Then you define the backend. How do you want to run it? So on Python with the Fortran backend, if you want to run on CPU or GPU, or even if you want to run multi-node. Actually, the multi-node version is still under development, so it's not really ready, or better, you can run it, but it's not super optimized for Leonardo yet, while you can run single node both with CPU and GPU. Then you can just run the simulation and obtain your results and analyze them. So it's pretty easy and straightforward. Now, just to show a couple of examples, here I show the example of the factorization of some prime numbers. They are not very big, but still it's interesting because the number of qubits we are gonna talk about is up to 72, which is not available with a state vector simulator. And as you see, a lot of time is taken by the preprocessing, writing the very non-local Shor algorithm in a form that is easy for the MPS, but then the computational time is not bad. And these are the bond dimension used. Just to give you an idea, the number, the 72 qubits are connected to the number 581 to be factorized. Something that comes to mind immediately is that the GPU here looks slower. Well, it's just because it's a small matrix, because the bond dimension is 64. And to better analyze it, we remember that one of the important part of Shor algorithm is the QFT, and try to analyze a QFT on a highly entangled circuit. So we start with a random MPS at bond dimension chi-half, so with a highly entangled, and we want to see on 100 qubit if the GPU is going to be better than the CPU running. And of course, at a certain point, the GPU starts to have a significant speed up. And just to put it in the same framework, this was the point where we were previously with Shor. So we were below the speed up, but if we start having a bond dimension of order of the thousands, well, then the GPU is really important. And just to compute the QFT on 100 qubits on 1,000, 2,000 of bond dimension, order of 10 to the 4 seconds. So pretty fast for the number of qubits involved. The library has already been used in several publications. For example, the study of entanglement and reproduction in quantum neural network, a study about a digital twin for Rydberg atoms, or the latest simulation of lattice fermion theories. And the last thing I want to talk about before ending is a result about efficient sampling of tensor networks that is gonna be released soon on the archive, hopefully next week, otherwise after Christmas probably. So let's suppose we have a probability distribution that is encoded in our quantum state. This is the exact. What you would do with an experiment is single shot that slowly builds your probability distribution. What you do on average, normally, if you do sampling with tensor networks, you get your shots, which is highlighted in red, and you get instantaneously the probability, the real probability of that state, but those probabilities, you will sample again the same state with the same probability. So you can end up doing some contraction, a lot of contraction for the state, for example, 1, 0, 0. Here we ended up in it 4 times. So we have some, let's say, additional computation that is not really important. And now, using some tricks, I will show you how we optimize it. So we divide the probability interval between 0 and 1 in sub-intervals that can be done due to the ability of having the conditional probability in tensor networks. And let's say we measure this interval related to 1, 0, 0. Well, if I know I measure that interval, I'm gonna remove it from the sampleable space in such a way that the next sample will be on something that I never seen before. And again, once I sample it, I remove it from the sampleable space and I go like this iteratively. Again, this can be done just because we have access to the conditional probabilities of every state through the measurements. I know it's a bit involved, but there will be a paper on this if you are interested in further information. And just to give you an idea of how it can speed up things, well, let's suppose we have a GHZ state plus some noise, and we want to understand how much the noise is important, so we want to sample the noise. Now, if we go for this, and in this plot, I will show on the y-axis the coverage, so how much of the probability I've measured, the maximum is 1, and the super iteration counter is just something proportional to the red dots. As you see, with the standard, since we are going to sample many times the GHZ, which has the 0.996 of probability, it's going to take a long time to cover the whole space of the noise. While if we are going to cut away the already sampled intervals, just in 2 iterations, we are basically at convergence. So just to conclude, NPS simulations are not limited by the number of qubits, but by the entanglement of the system. There is an easy-to-use Python frontend for the HPC-ready backend, and the module is available on Leonardo. You can just module load it. So thank you for your attention, and thanks also all my collaborators for the emulator, so both from the Padova side and the Qmatchatea side. This is the website of the Python packages with the documentation and all the open source code.
Thanks. Thanks a lot. Is there any question for Marco? Christian, can you? Okay, Lara, thank you.
So I wanted to ask for the GPU speed up. If you can say, where do you find the most speed up? So it's the instructions or actually the SVD routines, or?
I think that it comes from the contractions at the moment, because the SVDs doesn't get a very big speed up in the GPU. You should go for another type of decomposition to see more speed up. Okay. For example, I mean, it's not yet implemented, but the idea is to go for eigen decompositions, and those should have an even better speed up. So this plot will get even better once we go through it.
And here, the one I mentioned, the critical one, where you get speed up?
It's around 2 to the 7, so more than 100. No, more, yeah, around on 500 more, you will get the speed up for sure.
Okay, thank you.
You're welcome.
Anybody else?
Hi, thank you for the nice talk. I have a question. Do you have some strategies to deal with parameterized circuits, for example?
I mean, at the moment, there is no strategy for the optimization. That is something we are gonna tackle sooner or later, but it's not in the near plans. if you're just interested in running the circuit, I mean, you bind the parameter, you run the circuit, and then you optimize it, but there is not yet a strategy for using the MPS structure in order to improve the optimization speed.
Okay.
Okay.
They're not.
So, yeah.
Thank you.
Please, Enrico.
So this workshop has two traditions. One is being before Christmas. The other one is ending before time of the schedule. So we are 3 minutes in advance, like every year. And before we conclude, I would like to say that in all the conferences, there's always a guy which does most of the work, much more of the other, who really takes care of that. And in this conference, this guy is Daniele. So I would like to ask you to thank him. Thank you, Enrico, but this is the truth.
Maybe last year this time is not so true because I have a very big team, very good team, and I want to thank.
Let's thank all the
I
team.
want to thank all the team, in particular Sara and Gabriele. It was the first HPCQC conference for them. I want to thank Christian for the help, for the organization, because all the local organization was on him. And I want to thank Riccardo. Where is Riccardo Mengoni? He's not here, okay, because he's going to another, maybe anticipated, but something. I want to thank him for being with us. I want to thank, of course, all the speakers. And of course, I want to thank all of you for being here, for making it possible and very beautiful. Thanks a lot. See you next year.